All right, good afternoon, everybody here in person and for those of you online as well. Really appreciate you being here for this special RAL M-Cube joint seminar. And we have a guest speaker here today from down the road at NLR. He's based out of Boulder. His name's Miguel Sanchez Gomez, a researcher there, and has been doing work there since 2023, right after he got his PhD. Just going back in time, Miguel did his PhD in the Atmospheric and Oceanic Sciences program at CU Boulder, worked under Julie Lundquist, who's a great friend of the lab and has done a lot of great collaborations here, as is Miguel himself. And he also got his master's at the same program at CU Boulder, but under mechanical engineering in 2019. And prior to that, he was at the University of Los Andes in Colombia, where he did mechanical engineering for his undergraduate. So like his PhD advisor, Miguel has collaborated extensively with RAL over the last few years, including with Sue Hop's research projects and also Jeremy Sauer and Domingo Munoz Esparza on fast eddy. And already looking at his publication list is very impressive amount of publications since his PhD and during his graduate program. He's done work in all kinds of areas, including wind turbines and other critical infrastructure and how that interacts with the boundary layer. And has worked in areas including large eddy simulation, mesoscale simulation, observations, data-driven methods, and has done a lot of great work on all kinds of different applications with wind turbines and wind farms. Recently, he's been doing a lot of exciting work on the hurricane boundary layer, first to look at offshore wind, but also other infrastructure and basic dynamics of boundary layers too. And his work on super resolution LES and hurricanes, I would claim is at the cutting edge and is not only shedding light on hurricane impacts on infrastructure like wind farms and other things, but I think will provide essential data sets for the community to help build the basic understanding of hurricane dynamics, which are so sensitive to the boundary layer. And so I'll stop talking here and hand it over to Miguel.
Chris. Hi everyone, and thank you, Chris, for the introduction. So today I want to show you some of the work we're doing where we use high-fidelity simulations, mostly of extreme weather, to improve the design of infrastructure. And we're going to focus on one particular set of infrastructure, wind turbines. But this can be applicable to a lot of energy assets as well. And this work is highly interdisciplinary. So I'm going to be showing work that's led by myself, other work that's led by some of my co-authors, which are listed here. So let's get going. OK, so first I want to start by looking at where tropical cyclones actually occur. So here on the map, we have the tropical cyclone tracks for the historical record. And I want to point out that we have this high concentration in the North Atlantic, also the Western and Eastern Pacific, and around India, and some concentration also near Australia. Now, where do we actually have wind and solar power plants? Turns out it's also within those regions. And Europe, but in Europe we don't have tropical cyclones, so let's just not focus on Europe yet. Now, we have a lot of wind turbine and solar generation in Japan, Southeast Asia, Eastern US, and Gulf of Mexico, and some concentration in India. And when we overlay the cyclone tracks with the actual deployment, we see that there's a high correlation, or there's bound to be some interactions between the tropical cyclones and these deployments of renewable energies. Now, this is current deployments. How about what's going to happen in a couple of years, couple of decades, future deployments? They actually look fairly similar. You have, again, high concentration in Europe. We're not interested in that. But you have very high concentration in Japan, Southeast Asia, and also in the US East Coast and Gulf of Mexico, or Gulf of America. And again, let's overlay the future deployments with the tropical cyclone tracks. There's high probability that at some point, those deployments might experience a tropical cyclone making landfall and impacting those assets. Now, what happens when a tropical cyclone, it can be a typhoon or hurricane, moves over a solar plant. This has happened a couple of times, actually. So one example is Hurricane Maria in 2017, here on the left. It made landfall in Puerto Rico, and it caused destructive damage to this wind farm, to this solar plant, I'm sorry. Interestingly, there were some panels shielded by this small mountain, small hill over here, and those panels were completely perfect, completely fine after the passage of Hurricane Maria. But on the other side, you have complete destruction of the plant. Similarly, Typhoon Ragasa here on the right also made landfall in China and caused catastrophic failure of the solar panels. These were offshore. It destroyed the substructure of the solar panels. Now this is solar. Now let's talk about wind. This has also happened a couple of times. You have tropical cyclones either making landfall or moving over offshore turbines. One of those was, again, Hurricane Maria, 2017. It moved over this wind farm right inside the eye wall, right at the eye wall of the storm. And it caused, again, destructive damage. You can see here, blades were destroyed, partially destroyed. Back here, you see a turbine that the tower buckled. And this was widespread across this wind farm. And similarly, in 2024, Typhoon Yagi made landfall in China and also caused a lot of problems with the wind farm. You have a lot of towers buckling as the tropical cyclone made landfall. But interestingly, the blades didn't suffer as much. You see that where the turbines that are still standing, the blades remain intact, or at least appear to be intact. Another example in 2003, in this case, some turbines were even ripped off the foundations. But again, widespread damage in Japan during Typhoon Miami. Now, before we move forward, let's cover some basics on wind turbines. So here on the left, we have this illustration of a wind turbine. So for our purposes, we're interested in the hub height, which is the center of the turbine rotor, which in modern turbines is about 100 to 150 meters. And we have the rotor diameter, which is the area covered by the blades as they move, which is on the order of 240 meters. So these are very big machines that span the lowest 300 meters of the boundary layer. And on the right, we have a power curve for a turbine. So for very low wind speeds, the turbine is not operating. As the wind speed increases beyond this cutting wind speed, it starts operating. And then as you get to the rated speed, you get to the generated rated power, and then your power output remains constant. And finally, at about 25 meters per second, your turbine shuts down for safety purposes. So during a tropical cyclone, you might expect some turbines to be operating during the passage of a storm. But during the tropical storm, some turbines might be operating. During a tropical cyclone, most of the turbines will be offline, idling and just tracking the storm as it passes over. Now, how are wind turbines actually designed? What are they designed to withstand? So this is going to be a very brief and incomplete course on how wind turbines are designed and how you choose them. But basically, the International Electrotechnical Commission, it provides design standards for turbines, offshore and onshore. And you have this little table right here. So what we're interested in is you choose a reference wind speed. In this case, the reference wind speed corresponds to the wind speed at a particular location with a 50-year recurrence period. And then based on the climatology of that particular location, you also choose a turbulence intensity. And then you match those two, and you choose a turbine that is designed to withstand that particular reference wind speed and that particular turbulence intensity. So let's take the United States. And let's say we're going to choose a turbine for this location. And here in the colors and contours, we have the 50-year return for the hub height wind speeds for the US. So this corresponds to a wind speed of about 90 miles per hour, or about, I believe it's 40 meters per second. So you would go back to the table, look at and find the reference wind speed corresponding to that return period, which would be 42.5 right here. And you would select a class, in this case, it would be a class 2 turbine, and you would put it right here. That's perfect. Now, what if you are planning to deploy wind turbines near Houston, where you might have tropical cyclones moving over, And the 50-year return period in this case is about like 120 miles per hour. So you would need a reference wind speed of about 57, 55 meters per second. But since you are in a region where tropical cyclones might occur, you directly go to this tropical class. So reference wind speed would be 57 meters per second. You have to deploy a turbine that is rated to withstand that reference wind speed. Okay, you chose your turbine. Now, what manufacturers usually do is they design the turbine to withstand certain atmospheric conditions during operation, during shutdown, and during extreme wind conditions. For this talk, we're only focusing on extreme wind conditions. So for extreme wind conditions, they do something that's somewhat simple. They use this mean wind speed model, which is just a power law wind profile, which with an amount of turbulence in the flow, and they just push this through an aeroelastic simulation to look into the loads. And if you look at the profile, there's no wind veer. It's just simple power law profile with constant turbulence across the entire rotor layer. So very simple. And it's a very highly simplified version of the boundary layer that is used for wind turbine design. And the problem is, whether you're deploying your turbine near Houston where tropical cyclones can occur, or right here where there's no tropical cyclones, you use the same engineering wind models. You just change the reference wind speed, which scales up and down the wind profile. Okay, so what we want to do here is we want to inform those engineering wind turbine design standards. And we want to do that by using high-fidelity simulations. So throughout the talk, we'll be first presenting this framework to very accurately capture the evolution and the turbulent winds within the tropical cyclone. Then we'll be studying the wind turbine response to the passage of a storm, and we'll compare that response to what wind turbines are actually designed to withstand. And finally, we'll be looking into those engineering wind models again to see which aspects are they actually capturing and what are they actually missing from, in this case, tropical cyclones. So let's start with the numerical framework. So this is based on this article right here. For the numerical framework, we're going to focus on Hurricane Laura. So Hurricane Laura provides a suite of observations for us to validate our simulations. And Hurricane Laura moved over the North Atlantic, made landfall in Cameron, Louisiana as a category 4 storm. And here is a nice visualization of Hurricane Laura before landfall from radar observations, airborne radar observations. And the way that we do the simulations is we use this precursor mesoscale simulation. We use a 2-domain setup. The outer domain covers the North Atlantic, and we have this box that tracks the location of the hurricane, this vortex following grid. So as you see here, the historical track is represented by this dotted, the black line with the colored dots. And our simulated track is represented by the white dots. So we are able to capture very well, at least at this point, the track of the storm, the historical track. And how we do this is we apply spectral nudging to the outer domain, and that constrains the movement of the vortex following grid as it evolves, as the hurricane evolves. However, the vortex following grid is not, we don't use any nudging in the vortex following grid, so you are able to develop a distinct structure within that smaller box. And we have this precursor mesoscale simulation. It's a vortex following grid, so the storm is always at the middle of this little box. But if we want to do high-fidelity simulations, we want to have the storm move over a virtual turbine position. So the reference frame is different. So what we do is, if you want to simulate LDS within this little box, we're going to interpolate this moving box onto this fixed grid. And then using WRF tools, we're going to develop initial and boundary conditions to this static domain, where instead of the hurricane moving with the grid, it will move across the grid. So this is how it actually looks like. On the left, we have the precursor mesoscale simulation, where the hurricane is always at the center of the domain, and the domain is moving with the storm. On the right it's a fixed grid and the hurricane moves across the domain. And in this case, we use an LES domain with a grid spacing of about 30 meters. So pretty high resolution LES. And the structure and the evolution of the storm that's capturing the mesoscale hopefully translates also into the LES. So if we capture the mesoscale pretty well, the mesoscale is also going to capture the large-scale structure of the storm fairly well. Okay, so what we want to do is we want to develop very accurate simulations that we then want to use for to improve wind turbine design. So we need to validate our results. And let's start by looking at the winds near the surface. In this case, we're looking into the synthetic aperture radar data on the left and the LES on the right. And for the LES, we're doing some spatial averaging to match that of the synthetic aperture radar data. So just by looking at the velocity contours, we have similar colors, so you would expect similar magnitude of wind speeds. But when we do an actual representation of the radial structure of the storm, we find that we're capturing very well the radius of maximum wind speed of about 20 kilometers, and also the wind speed at the wind speed distribution across all radii. So we're doing a good job at capturing the structure near the surface. And I forgot to mention the blue is the mesoscale, the red is the LES. So they're also fairly similar. Now, how about the winds far aloft? In that case, we use the airborne radar data that I showed at the beginning. And on the left, we have the radar data for the radar data, and the right, the LES data. And if we sample a profile at the radius of maximum wind speed, here are the results. Again, our simulations are capturing very well the vertical structure of the storm for the LES and the mesoscale. And now if we sample along the radius at a height of about 2 kilometers, we see the same thing. Our simulations are doing a very good job. Now we know our simulations are capturing the structure at the surface and about 2 kilometers or so and above. But how about those heights in between, the actual boundary layer, where you have all that turbulence that we're interested in? In that case, we compare our simulations to dropsand observations. And in this plot, we have a lot of panels, a lot of colors. Each color, each panel represents a dropsand dropped relative to the storm. And you see the actual location of the dropsand here in the bottom right. So what I want to highlight is that the LES, which is the solid line, and the dropsand, which is the dotted line, they actually agree pretty well across most of those azimuth locations. So in some cases, you might have this narrow jet, for example, near about 200 meters in both the LES and the dropsand data. In other cases, of the other azimuth angles, you might have this very broad jet that is also, again, well captured by the LES data. Okay, so we have some simulations that are capturing very well the structure of the storm across all heights. Now, how can we use this for wind turbine design? Well, wind turbines have, like I said, a diameter of about 240 meters. So LES at 33 meters might not be fine enough to resolve those very small scale features that affect wind turbines. So what we do, and I'll play that again, is that we add a refinement region within the northeast quadrant of the storm, where you might expect those faster wind speeds. And the refinement region is at about 10 meters grid spacing. And we sample the velocity field at these three radial locations as if we were a wind turbine. So we want to evaluate if the coarse LES results, which are 30 meters, match with those of the fine scale LES across mean wind speeds and turbulent characteristics of the flow. So here we have the mean wind speed profile on the left, the vertical change in wind direction, the wind veer on the middle, and the TKE in the flow on the right. So when we look at mean characteristics, they're actually very similar between both the coarse and the high resolution LES. But then when you jump into turbulence statistics, in particular TKE in the flow, there's big differences in the amount of turbulence captured by the simulations. And I forgot to mention, this is also across the three different radial locations. But I want to highlight that, especially for TKE, And this black solid line is very different to this dotted black line. So why is this actually happening? What we find is that with this coarse LES, which is actually 30 meters, is actually very fine resolution LES, we're not capturing the inertial subrange of the flow at hub height, at 150 meters. So here's the turbulence spectra for the coarse LES, the solid line, and the fine resolution LES, the dotted line. And when we actually find the inertial subrange, which is shown here in the fine LES, we see that the coarse resolution simulation cannot capture that inertial subrange. So the transfer of energy, of turbulent energy across the scales is truncated, and therefore you get this sort of accumulation of energy at the large scales of motion. And this might be impactful for wind turbine design. How am I doing on time? I'm going to skip over this slide, but basically shows that it's also important to capture the, let me go back. So here we're going to look into the spatial coherence of the flow. So this is looking into how one eddy, let's say at this location, correlates in space and time with another eddy at this location. If they're highly correlated, then this function right here would be equal to 1. If they're not correlated, it would be equal to 0. So when you have highly correlated eddies, you might imagine that if a wind turbine blade sees one eddy that's highly correlated along its span, it might experience very different loads than if it were subject to a bunch of small eddies that are uncorrelated over time. And what we find is that the spatial-temporal correlation of the flow is very different between the high-resolution and low-resolution LES. I'm going to leave it at that, but I'd be happy to take questions on that. Now, how can we actually use these simulations, these results, to improve wind turbine design? Well, first, we want to address the question of what are the loads during the hurricane. So we're going to use, again, this mesoscale precursor simulation. We're going to use another LES, coarse LES domain, in this case, coarser than the one before, to cover the entire evolution of the hurricane over a 5-hour-long period. And finally, we're going to go down to 10 meters at some locations to do some wind turbine loads analysis. And in fact, this turbine scale LES, we're using fast eddy, which was developed here at RAL. This is how it actually looks like. This is offline coupling all the way. So we're going to focus mostly on the turbine scale LES. But instead of looking at just one location, we're going to investigate how the turbines might experience the storm from different locations relative to the storm's motion. So we're going to look at what a turbine over here might experience compared to one that experiences the actual eye wall passage. And the response might be very different in both cases. So we want to cover a broad range of conditions. Now, here we have the actual hub height wind speed, wind direction, and turbulence in the flow that a wind turbine at each of these 7 radial locations experiences. In red, we have locations to the right of the storm, these ones right here, and in blue, locations to the left of the storm. So what you see is that the maximum wind speed that a turbine experiences, even during the same passage of a storm, is going to vary a lot depending on how far you are from the storm center. So in some cases, you might experience maximum wind speeds of 50 meters per second, in the other ones, 80 meters per second, and the loads are expected to vary as well. And this holds true for turbulence as well. Okay, so we have all this data. Now we're going to see the wind turbine's response. So this animation, it shows how a turbine at this location experiences the passage of the storm. So as the storm gets closer, here you have the wind turbine loads. In this case, it's the tower loads. You saw some turbines buckling, so we're interested in the loads on the tower. And as the wind speed increases, the loads start to increase. This dashed line represents the moving maximum in the loads. So the moving maximum is increasing as the eye wall of the storm approaches, and is reaching a maximum as the leading edge of the eye wall impacts the turbine. And let's wait a little bit longer. So now you have the eye wall of the leading edge of the eye wall of the storm impacted the turbine position. You get massive loads on the turbine structure, and then inside the eye, very slow wind speeds, very small turbulence. Then the loads basically don't change over time. But all the time, what we're doing is the turbine is following the mean wind direction. So we're assuming the best case scenario for a wind turbine during these conditions. And then later, the trailing edge of the storm of the eye wall moves over to the turbine, and you get again an increase in loads, but not as dramatic as for the leading edge of the eye wall. Okay, let's wait a couple of more seconds for it to move forward. Okay, so we do this for all the 7 locations. This is just showing the radial location at the center of the storm. We do this for all 7. And these are the actual loads on the turbine structure. So on the middle is the blade loads. On the bottom is in the middle is the tower loads. In the bottom are the blade loads. There's a couple of things I want to highlight. The maximum blade loads, they don't happen at the same time as the maximum tower loads or at the same radial location. So in some cases where you saw in the previous slides, some blades being destroyed but the tower remained intact, might be because of the spatial heterogeneity of the flow within the tropical cyclones. And you can also see that if you are at a radial location pretty far from the storm, your loads can be 4 times smaller than if you are impacted by the eye wall of the storm. There's a lot of spatial heterogeneity that also translates into the turbine loads. Okay, so we have this data set where we have the actual turbine response to a storm passage. Now, how does this actually compare with what turbines are designed to withstand? Again, let's look at the table. We're going to choose a wind turbine that's rated for a T-class wind turbine that could, in theory, withstand the tropical cyclones with the highest possible turbulence intensity. And we're going to do some simulations, aeroelastic simulations of the loads using the design best practices. So we use this mean wind speed, again, a power low wind profile, and this representation of the turbulence. So here on the left, we have the loads, the maximum loads on the tower at the bottom and the blades at the top. Let's not focus on the different color chart bar graphs. For the LES inflow as a function of radius. So the maximum loads are at this radial location of 1. That's basically the eye wall of the storm. And they decrease on the other side of the storm, to the left of the storm. Now, these are the design load cases. This is what wind turbines are designed to withstand. These are the loads that a wind turbine would experience with those simplified engineering wind models. And if you compare what the wind turbines were subject to during Hurricane Laura, during this representation of Hurricane Laura, with what they're actually designed to withstand, there's a very big difference, especially if you're closer to the eye wall. Now, what might be driving these differences? We're using the same turbine model. We're just changing the inflow conditions to the turbines. In one case, we're using the LES inflow. In the other case, we're using this synthetic inflow from the engineering wind models. So if you look at the models, there's a lot of constants to represent turbulence and the mean wind flow. So we're going to explore how these constants differ from our LES inflow and which of these might be important to capture from the LES inflow that translate into the larger loads in the turbines. So there's a lot of information in this slide, but what I want to show is that for this set of parameters, we're going to go on one hand, the engineering models, on the other one, the LES, and we're going to evaluate the space in between, that hyperparameter space, to see which conditions are driving the differences in the loads between the LES-driven simulations and the engineering wind model-driven simulations. So when we do this across the whole hyperparameter space, we find that there's only certain variables that are important for the actual turbine response during the tropical cyclones. So let's start with the mean wind speed. As you might expect, faster wind speeds are going to drive larger loads. That's expected. but you also see veer pop up. And I forgot to mention, the orange is for the tower, the loads on the tower, and blue highlights loads for the blades. So veer again, and the velocity variance for the V component, the length scale of the V component, and some turbulence characteristics again of the V component. And finally, how misaligned is the wind turbine to the incoming flow. So when you take a step back and compare all of these parameters that are important for the design load cases, you see that the V component is the common denominator except for the mean velocity. So when we go back to the standards assume zero mean V wind speed, which is veer. In our simulations, veer is actually pretty large. And we also find that the velocity variance of the V velocity component is much larger in our simulations compared to this simplified engineering wind models. So, and then there's this AV and BV, which are related to the spatiotemporal coherence of turbulence. So to sum up, what we did is we used this multi-scale numerical framework to capture the large scales of motion within the hurricane and the turbulent features in the flow relevant for wind turbine scales. And we applied those for wind turbine load calculations and to look into which features in the flow are important for wind turbine design. And thank you very much. I'll take any questions.
All right, thank you. That was an awesome talk. Lots of time for questions. Also online, please feel free to use Slido. Quick question while people think of some good ones. Do you know the mosaic method that you used for the part one looked really useful? Do you know if that's a community tool or something that's part of the WRF system now?
It's not part of the WRF system. It's a bunch of Python notebooks, but those are available. Yes.
Cool.
Yes.
Yeah, thanks very much. I just wondered why you chose to simulate a real case like Hurricane Laura rather than an idealized case. Because I was just thinking the mesoscale model, you know, once it starts running along the track, it could do what it wants and develop like eyewall replacement cycles or random like rapid intensification, which would throw off like the realism of the case. So I just wondered the value of that.
So I think there's multiple aspects to that. Let's start with the idealized simulations. So the idealized simulations, you would develop some sort of steady state cyclone. And that's great. That's actually how we started this set of experiments using idealized simulations. And we found that there were deficiencies in the standards, but the idealized simulations don't capture that translation. And when you have translation, we found that the actual structure, the actual magnitude in turbulence, actual vertical structure of the wind fields near the surface within that turbine neutral layer changes azimuthally within the storm. So those can be very useful, but they don't capture the complete picture. And regarding the mesoscale, that's why we focus a lot on validation for this particular case. When we validated our results very close to the time we simulated the LES as well. So we try to match the time of the observations with the time of the LES to make sure that we're actually capturing very well the structure of the storm to then follow up with the design standards. Yeah.
Yeah, thank you. Yeah, that makes sense.
All right, see if I have a good aim.
Yeah, thanks for the talk. My question is about the difference between the 33 meter and the 11 meter LES. So you showed that mean wind speed wise, there's actually not much difference, but then in the turbulence statistics, there was quite a bit difference, and you related it to that you need 10 meter grid spacing to resolve the inertial subrange. I'm wondering, do you have any observations that you could use to validate whether it's really true that the 11 meter domain is better or more realistic than the 30 meter?
Unfortunately, it's hard to come by with turbulence measurements during the hurricane. especially at about 100 meters or so, which is where we're interested in. So, but what we did instead for another case is we did a convergence study on the grid spacing when we went from 55 meters down to 5 meters. And we found that the turbulence statistics and the actual response of the turbine as well, they converged after between 10 meters and 5 meters. So, but yeah, observations would be great.
Yeah.
They're hard
On
to
that
come
note,
by.
I'm wondering if some folks in the M-Cube lab here, they have collaborated with NOAA on the drones that they launch out of the Hurricane Hunter aircraft, and they're supposed to fly at very low altitude.
Okay.
And somebody here may know better than me if there's already some measurements out there, data sets published. I'm not sure. I know there's some preliminary studies, but that may be one way to actually get real data through these drones that, yeah, I think it's called the S0. And yeah, people are still working on it, but maybe that's the future, use drone observations.
For sure. There were actually radar observations for LoRa, but they were at landfall. And we weren't able to capture we captured the landfall location, but even if you move by 10 kilometers, and due to the spatial heterogeneity of the land use and surface roughness, it was very hard to do a one-to-one comparison between the dual Doppler radar observations and our LES. So that was the closest we could get to finer scale observations, but yeah.
We have a question online from Ben Barr. Great presentation. Do any offshore turbine design standards account for loading due to ocean waves and surface currents?
Yes, great question. And they actually do account for ocean waves. And that's actually very important for offshore wind turbines during tropical cyclones. You have ocean waves as the storm moves through the turbine. We did not include those in our simulations, but the standards do include those, but they are only, so in the standards, the way that they account for those is through statistical coupling between the wave field and the wind field. So there's also room to improve that the ocean wave and wind field coupling within the design standards. Yeah, but that's definitely important.
Hi, this was a wonderful talk. I was interested if you also did similar measurements, maybe like also closer to land, where you also might get a little bit more like off-land flow that could induce additional turbulence. Because I know this is kind of a little bit more further out in the Gulf, it seems.
For this case, we didn't do any landfall scenarios. We're considering those for 2 other cases, but that's our natural transition to look into the coastal turbines. All the turbines that I showed at the beginning were actually at the coast. So there's also that ocean to land transition,
Right.
and we need to understand that better to also improve the standards for those conditions. But in this case, we didn't look into the
Okay,
near
thank you.
the coastline.
Great talk, Miguel. About a month ago, we had another hurricane talk by Xiaomin Chen, who was visiting, and he was studying landfalling hurricanes and impact on structures on land. And he made the point that gusts are the important metric to be looking at. Now, that's, the IEC standards look at average wind and at turbulence intensity. How does that I seem to remember from one of your early papers, you did some gust studies. How do you translate from the IEC variables into gusts and back and forth? And what is most relevant? What should IEC be using?
So I think the gusts are very relevant. They are actually, when you look at the design codes, they're actually based on gusts. the IEC standards for turbines, they have the option for using mean winds or gusts for design. But for offshore turbine design especially, manufacturers prefer to use the mean wind conditions. I'm not sure if there would be a difference in the turbine response or in the ultimate loads in the turbine if you were to use gusts instead of mean winds. So in the standards, you use a 10-minute long simulation, which includes gusts. It's you evaluate the time series evolution of the loads, so it's a dynamic response. So you're including gusts within the simulation, but you're including the entire duration. So that's a long way of saying they're both important. I think they go back to the way that they've been doing things initially for the IEC, for the wind turbine design. But I think if you were to combine designs, if you were to have a more uniform framework for design of infrastructure in general, going to the gusts would be better because that's how ASE, the standards design codes, were originally developed. That's how they've been continuously developing. Right now, for the IEC, you're just using a gust factor of 1.4 to go from 10 minutes to 3-second gusts, which is questionable in many cases. So I think different methodologies, maybe they can produce the same results, but that's a good question. I'm not sure.
All right, we have a question from Rosie.
Hi, very nice presentation, very cool animations too. It seems to me that Laura was more or less well-behaved, right, during this time period. Have you thought about expanding your study to add something like a tropical cyclone undergoing rapid intensification, or maybe a shear tropical cyclone where the winds may be asymmetric, and depending on where the storm goes, then that would vary a lot what the turbines may experience? I imagine it would be extremely complicated to get all of that, but I'm just curious if you've thought about something less well-behaved.
Yeah, you make a good point. That's actually one of the reasons we chose LoRa. The track was somewhat easy to simulate. You look at Harvey, for example, the track does some very weird stuff. But we're expanding to cover more storms. First, we want to cover more intensity levels. Right now, it's just one category 4 storm. We want to cover more intensity levels and more geographic locations. So not only the Gulf of Mexico, but also the East Coast. But I think that would be the stage after, what you're mentioning is, that would be the next stage after the covering broad range of storm intensities, because it's like the most complex scenario for simulating,
right,
in both the LES and the mesoscale. So, but yeah, we're moving towards that.
Cool, thank you.
All right, we have a question online from someone you might know, Julie Lundquist. Great talk and work, Miguel. Could you address how many different storms would need to be simulated? How representative are the results? And are there ways to use AI/ML to generalize the results?
So I think this touches a little bit on what we were just talking about. This is just one case, one intensity level, one geographic location. If you go to other locations where the background thermodynamic profiles might be different, wind shear might be different, then you might get slightly different results for the actual simulated loads on the turbines. So, like I was saying, we plan to cover a broader range of storms to get an understanding of the spread of the turbulence and wind field characteristics. And so I would say these results are not as representative. They're just an initial stage. Are there ways to generalize using machine learning? Yeah, I think AI could be machine learning surrogates, or super resolution models could be a good alternative. We would have to train those, so we're also working on training those. But when you train those, you have to generate a lot of storms. So at some point, it can become counterproductive. But you were looking at some of those very nice animations. Those are extremely expensive simulations, especially when you go down to the 5 meters, 10 meters cases. So I think machine learning, artificial intelligence, super resolution methods, they can either complement the LES to expand the cases, or at some point, they might even replace the LES to provide some more cheaper alternatives to simulate these storms. So yeah, these are options that we're exploring to make these results more feasible and more useful for the broader community. Yeah, but a lot of work still to be done in this area, definitely.
All right, lots of great questions so far. Is there any? Okay, we got one more. All right, ready?
Hi, Mughal. This is Nazla. Good to be at your talk once again. My question is that all those wind speed, are you considering the turbine is running or stop, and how these choices can impact your load result?
I'm sorry, am I considering what?
Are you considering that turbine is running or
okay.
stop, and
Okay.
how these choices change your load result? Another question is, inside a hurricane eye, the wind flips, right?
Mm-hmm.
So is the turbine can fast enough to capture that change? Like, how you think about that?
Those are great questions. So in this case, so what happens when a hurricane actually moves or comes closer to the turbine is you might get the grid shutting down. So we're assuming a best case scenario where we're assuming the turbine has battery backup. That's actually a requirement for many locations. You have a battery backup so that the turbine can, although it's not operating, it can stay aligned with the predominant wind direction. So the yaw controller that's aligning the turbine to the flow is always active. If you get misalignment, very large misalignments, then it's probable that your turbine won't survive. So we are keeping that yaw controller active. The blades are feathered, so they don't produce any power. There's also the question, which is the best feather angle for mitigating loads? I think that's a very interesting topic that we're not addressing right now. And like you mentioned, as the eye wall moves over the turbine, the wind direction changes. So with the yaw controller, we're actually able to track that mean change in wind direction because it's over more than 10 minutes. So the yaw controller is able to keep track of that mean wind direction pretty well. Yeah.
Wonderful. Thank you so much.
All right, we have one more question online from Derek Roberts. Great presentation. Can you speak to if or how you are working with industry groups to translate turbine loads risk associated with boundary layer complexity to improve design specifications and standards?
Yes, this is a great question. So I think for the risk community, what we're trying to do is convey the message that it's not, so for the risk community, how you develop those 50-year, 100-year return periods, it's, I would say, somewhat simplistic approach. Those are usually developed at 10 meters and then extrapolated somehow to hub height. So we want to convey that the way in which you do that extrapolation matters a lot, and that it's not only a simple extrapolation and then you just get a hub height wind speed. The actual structure of the storm is very complex. So it's not plugging in a single number, but it requires more details to get to whether a turbine survives or not. So we're trying to convey that message to the risk community. But for the wind turbine manufacturers, it's hard to establish a two-way dialogue. It's usually one way. We provide some feedback and they think about it and then they don't say anything back. But it's a lot of trade secrets within the wind turbine manufacturer community. So it's harder to have a real impact on the manufacturers. That's why we're trying to address the standards directly, which the manufacturers would have to adhere directly. So we want to launch this IEA wind task on extreme weather and wind turbines to address the standards directly rather than going to the manufacturers themselves. Yeah.
Okay, I think we can wrap it up, but I just wanted to mention a few things. First of all, there's cookies up here. Please take some. And then second of all, feel free to drop by to ask a few extra questions. Miguel's in town, so please do get in touch with him. Great collaborator and a great person to talk to and learn from. Oh, we have a few more questions online, but I'll make sure to relay those to you. But anyway, thanks for the wonderful talk. Let's thank our speaker once more. Thank you.